Okay, are you on yet? Okay, good. All right, hi everybody. Today we're going to talk about greenhouse gases and work a little bit through this document that's on Teams, and I'll kind of show you what I mean by some of this stuff and what I want you to get out of it. So we'll just wait a second for streams to catch up, make sure everything's working properly. Good? Okay, great. All right, so as I mentioned in class today, we're going to look at the chemistry of greenhouse gases. What is it that makes a molecule a greenhouse gas? What does that even mean? And so forth. All right, so this document kind of takes you through these ideas and gives you some links to some references that you could use to figure some of this stuff out. So before we talk about greenhouse gases, we first have to talk about this, which is the electromagnetic spectrum. This is light. Now we think of light often just in this form right here, visible light, which is the light that we can see, but there's actually lots of different kinds of light, different types of radiation, and that produces a spectrum that we can graph, let's say, based on energy. So very low energy light is down here on the left, and those are things like radio waves that propagate through space. Then as we increase the energy and shorten the wavelength, we get microwaves, we get infrared light, visible light, which is all the light we can see, and then within that visible light, we can actually look at different parts of the visible spectrum. So for example, the lower energy visible light is red, the higher energy visible light is blue, and then purple. And then if the energy goes above that, we have what's called ultraviolet light, so like above violet in energy, so it's a little bit higher energy. And then getting up into X-rays, gamma rays, cosmic rays, these really, really high energy sources of radiation. Now we should define this term. Radiation, we're going to use that term. Sometimes it's kind of a loaded word because people associate it with nuclear radiation, which is the energy that's emitted by things that are decaying, like nuclear decay, or these tend to be fairly dangerous things. So sometimes that word radiation seems a little scary, but it actually just means energy propagating from a source. So that could be like when you turn on a light and there's light coming out of the light bulb, that is radiation. That is visible radiation that's being emitted by that light. It doesn't have to be dangerous. In fact, we can look at the spectrum and we can sort of find almost a line. So I'm going to erase my line from before. But this line between visible and ultraviolet light, it's not exactly a line, but above this, so ultraviolet, X-rays, all this stuff up here, we sometimes refer to as ionizing radiation. This is radiation or light that is high enough energy to knock electrons off of molecules, and this can cause some pretty serious problems when it interacts like with our bodies, for example. So that's why, for example, ultraviolet light, UV light from the sun can cause skin cancer because that light has enough energy that it can damage the DNA of the cells in your skin, and that can ultimately lead to some pretty bad stuff. Same thing with X-rays. That's why, like, as we've talked about with other things too, it doesn't mean that every single bit of this thing will hurt you, but like if you have to get a lot of CT scans or chest X-rays or things like that, they will keep track of that and say, well, like, well, you've already had this many of these this year, you probably shouldn't have any more because that X-ray exposure is not safe. If you're working around X-ray equipment, you're going to wear special protective equipment to make sure that your X-ray dosage doesn't exceed a dangerous amount, because that is light that can hurt you. Things like gamma rays, which often just cosmic rays which come from space, nothing you can really do about it. They're just shooting through space, and occasionally they hit us. That can sometimes be a problem too. So your radiation, your ionizing radiation exposure is higher when you're in an airplane, for example, because you don't have as much atmosphere protecting you from those high energy rays. So that's ionizing radiation. We're not going to talk too much about that because that type of radiation really doesn't have much to do with the greenhouse effect or climate change. The light that we're going to be most interested in is infrared and visible light. So that's over here to the left of our ionizing radiation. All right, so we already said visible light is the light that we can see, and infrared light is light that we cannot see, and it is lower in energy. And the reason there's like a heater here is that we often experience infrared light as heat. So for example, if you've ever been around a fire, like a good-sized fire, if you sort of stare directly at the fire, you can really like feel the heat coming off and hitting your face. That's not because the fire is hot and it's heating the air around it, which is then eventually getting to your face. That's because that fire is directly emitting infrared light, which is hitting your face, and then that we experience that as heat. So if you've seen things like infrared cameras, those work because anything with a temperature that's above absolute zero is emitting infrared light. And so the hotter something is, the more infrared light it's going to emit, and you can measure that and use that as an imaging technique. All right, so back to our thing here. Again, if there's any questions, you can put them in the chat or send me a note on Teams. So, whoops. So wavelength and frequency are two ways that we describe, or two things that we use to describe light. Wavelength refers to, if we go back to our picture here, how far is it between one, or how long is it between one, let's say, top of a wave and another wave. So as the wavelength gets shorter, the oscillation gets faster. And so that's why then frequency is sort of an inverse of wavelength. So the higher the frequency, the faster it's oscillating and the shorter the wavelength is. So there's a little bit more detailed diagram at this link here. So when you go through this document, you can find that and hopefully find some answers to your questions here. Okay, so the next thing that we want to look at is how light interacts with matter in a way that is absorbing or emitting heat. So this is where some people get really hung up on this particular activity. I think it's because these questions are actually simpler than they sound. So if 100% of the radiation of a particular type of light, that's what this wave number is, just a particular energy of light, is transmitted through something, how much is absorbed? And maybe I should reword this to be clearer. That this is, we're talking about transmitted through some matter, if 100% is transmitted, then that means none of it is absorbed. It all goes through without being absorbed. So that's really what that question is really asking. So then what's happening with this greenhouse effect? Well, broadly, we can draw a little picture of it. Oh, I don't have yellow. Well, I've got a yellow highlighter. Okay, so here's our sun. Okay, here's our sun, and then here's our surface of the Earth. All right, so the sun is emitting light, various types of light, but primarily we're talking here about visible light, the light that we see, and it hits the Earth. And just as you probably noticed, if you leave if your car has like a dark interior, or you leave something out outside on a hot day, on a bright day, the sun is going to heat that thing up. And that's basically what happens to the Earth's surface all the time, and actually to any planet's surface. The energy from the sun is hitting the surface of the Earth. So let's label some things here. So this is visible light. It's also UV and infrared and stuff, but primarily we're concerned right now with visible light. So light we can see, it hits the Earth, and that causes the Earth to emit heat. And as we just talked about, infrared light is kind of like heat. So when we talk about something getting hotter or warming up, we're talking about it emitting infrared light. So as the Earth gets irradiated, it's now able to emit infrared light. So the sun is emitting all this broad spectrum light. It's hitting the Earth, which is causing the Earth to absorb that light and then re-emit infrared radiation. It also reflects some visible light as well, but the warming part of it is the reflection of infrared light. So if we didn't have greenhouse gases in the atmosphere, that would be basically the end of the story. The infrared light would go out into space and the surface would cool. And that's what we see in other planets that don't have a greenhouse type atmosphere. So like, Mars or Mercury or something. In those places, even the moon really, the sun heats up the planet to pretty hot during the day, and then during the night it gets extremely cold as all that energy leaves. So on Earth, we have an atmosphere that's composed of lots of different gases: oxygen, nitrogen, water, um, and then carbon dioxide and some other things. And some of those gases, including carbon dioxide and water, but not nitrogen and oxygen, have the ability to absorb infrared light and essentially re-reflect. So the greenhouse gases in the atmosphere allow the infrared light to be absorbed and re-emitted back toward Earth. It's not exactly the same energy, but that's what's happening. And so that, in effect, traps the heat in our atmosphere and near the planet and allows for a more stable temperature. So we don't see the Earth, going down to negative hundreds of degrees at night as soon as the sun stops irradiating it, because we can maintain some of that heat. And that's what we call that greenhouse effect, that reflection of infrared light. And that's what allows us all to actually be here. If we didn't have that greenhouse effect, all that heat would escape and we would not be able to survive. So, in that way, the greenhouse effect is a good thing. It allows us to live. But as you've probably heard, in the past 100 years or so, we have emitted a lot of greenhouse gases into the atmosphere through the burning of fossil fuels, as well as things like livestock agriculture. And that has accelerated this process to the point at which the Earth is now warming to temperatures that are going to really dramatically affect how all the systems on the planet work. So in order for this whole thing that I'm drawing here to work out in our favor, it has to be balanced at a particular temperature that works well for us and all the systems that we depend on. If that gets out of balance, then we're in trouble, and that's where we see ourselves now. So let's zoom in a little bit and look at these molecules and why they can actually do this. So carbon dioxide is a molecule that we would draw like this. So a carbon atom with two double bonded oxygens. And as we learned a couple units ago, there is some polarity going on here because the electrons are pulled more to the oxygen than to the carbon. So if we think about, there's some like kind of negative areas around the oxygen, and there's kind of positive area around the carbon. I don't want to draw specific plus and minus signs because that corresponds to charges, but they're just kind of like these general fields. Now, overall, if you look at a molecule like this, those actually cancel out because the negatives are on the outside, the positives on the inside. The overall molecule ends up being fairly nonpolar. But imagine if we stretch out one side of this like this. So let's say this bond on the right got longer. Well, now those negatives and positives don't really balance each other out anymore because the positive middle has kind of shifted over to the left. So in this molecule or this version of the molecule, the left side is going to be a little bit more positive and the right side is going to be a little bit more negative. And it turns out that any molecule that can do this can absorb infrared light. So any molecule that can change its polarity by stretching or bending its bonds can absorb infrared light. So molecules that change polarity and we can say, we'll just say stretching or bending. A more technical term would be vibration. All right, so molecules that can change polarity through stretching, bending, absorb infrared light. So another example, let's look at water. Water also can do this. Water, the positive sides are more toward the hydrogen, and negative is to the oxygen. So water is actually always polar. It always has if we kind of cut through the middle here, we always have a negative side up here and a positive side down there. But if you can imagine if this molecule bends or stretches in different ways, either symmetrically or asymmetrically, that's going to mess with its polarity. That's going to change its polarity. And so that allows water to absorb infrared light as well. And then let's contrast that with something that doesn't. So oxygen is like this, O2, two oxygen atoms connected by a double bond. This is nonpolar because you've got oxygen and oxygen, so that electrons aren't going more to one side or the other. And so when this bond stretches, that's not changing anything about the polarity. And so oxygen, as well as nitrogen, which looks like this, don't absorb infrared light because they don't have that change in polarity when they stretch or bend. And so when we talk about molecules that can be greenhouse gases, there's, pretty much infinite molecules that could potentially act as greenhouse gases because it's a pretty broad category, anything that can change polarity. And most molecules can do this. But when we talk about the main issues in the atmosphere, we talk about these four gases: carbon dioxide, nitrous oxide, methane, and water. And the reason we talk about those four is not just because of the chemistry of their absorption, but also because those four are in significant quantities in the atmosphere to actually make this effect. So yes, there are lots of other ones, sulfur-based gases, whatever, other things like that, organic gases, but they're not at significant concentrations in our atmosphere to really make any difference. So these are the ones that most contribute to our climate. And so if the levels of those gases in the atmosphere increase, then you're going to have more absorption and re-reflection of infrared light, and therefore a warming of the Earth, which is why when we look at some of the data in the IPCC report, you'll see that the Earth temperature tracks very, very closely with concentrations of these gases. And why, if we want to do something about that, really the only option is to control the levels of these gases that are in the atmosphere. The biggest one probably that we hear the most about is carbon dioxide, and that's because that is a byproduct of combustion. So anytime we burn anything, we release carbon dioxide, and the biggest issue there is with our fuels. So we have fossil fuels, which are taken from deep down in the earth, which were originally mostly plants um, and algae and stuff like that from millions and millions of years ago. And then we burn that, and all of that carbon dioxide that those plants took out of the atmosphere millions of years ago is now back in the atmosphere and accumulating, and that's what leads to the rise in temperature. So, moving on to the next page, you can see some different processes where greenhouse gases are either created or used up in processes that are either natural or man-made. So for each of these, 10 processes, you should figure out which greenhouse gas involved, and it might be more than one. So it could be 2 or 3 greenhouse gases involved there. Sorry, I'm got a little bit of a delay here. And then, so for then, no, I don't want to do any of that. For each one, you should say whether it is a source or a sink for the greenhouse gas. If it's a source, that means it produces the gas. So we'd expect to see the gas on the right-hand side of the equation. So the gas is a result of this particular process. If it is a sink, that means it's something that's using up or like draining the greenhouse gas. So then we would see that on the left side of the equation as it's just like, sorry, the left side. My camera's reversed here. So it is something that uses up that particular greenhouse gas. And the 4 you're going to be looking for here are the 4 we just talked about: nitrous oxide, methane, carbon dioxide, and water. Okay, and then finally, and then if it's a source of a greenhouse gas, is it anthropogenic, meaning it's something that's a result of humans doing stuff, or is it just a natural process on Earth? Then finally, write a balanced chemical equation to represent each process. So we did balancing equations a while ago, but one thing we didn't really do is turning a sentence into a chemical equation. So for number 1, we can work on this one together. During respiration by plants and animals, a carbohydrate, in the example here is glucose, reacts with oxygen to produce water and carbon dioxide. Okay, so first, what greenhouse gases are involved? Well, I see 2. I see water and carbon dioxide. So water and carbon dioxide. All right. So number 2, is this a source or sink of these greenhouse gases? So we have to think about what's going on. The carbohydrate reacts with oxygen, so those are the things that we start with, and then we produce water and carbon dioxide. So if it's producing the greenhouse gases, then that is a source of the greenhouse gases. It's producing them from something else. Okay, is this anthropogenic or natural? I would say this is natural because all plants and animals are doing this without whether or not humans are involved. Humans also do this, by the way, but I think we can say it's overall natural. And then we're going to write this chemical equation. So when we write a chemical equation from a sentence, we have to think about what things did we start with, and then what things did we end up with? What did we produce at the end? So in this case, we're starting with this glucose, C6H12O6, and then we are reacting that with oxygen and producing water and carbon dioxide. All right, so there's an equation. It is not balanced. I'll leave it to you to do the balancing here. But then you can do that for each one of these, and it'll hopefully teach you some stuff about sources and sinks of greenhouse gases, as well as practicing chemical equations. All right, so next week we will talk about more about the IPCC report. Hopefully some people will have some more of a chance to read through that and have some questions, and we will likely discuss that in class rather than online. All right, thanks everybody.